There we go. Today we're starting our final lesson on thermochemistry. This is it. And today we're going to start Gibbs free energy. It's named after the physicist Willard Gibbs. As I said, he was a physicist. And he combined an enthalpy / entropy function that we call Gibbs free energy. Now, in these reactions, pressure and temp are constant. The symbol for Gibbs free energy, or you can just call it free energy, is G. That's going to be our variable. So we have S for entropy, H for enthalpy, G for free energy. Obviously, change in free energy is delta G. Free energy of a system is going to be G with system as a subscript. Remember, sub means below, super means above. You guys know superscripts as being exponents, subscripts are going to be on the bottom. All this is energy available to do work. All right. The free energy change of a system is equal to the difference between a system's change in enthalpy and the product of the Kelvin temp and the change in entropy. When I say difference, what type of math will we be doing? That's going to be a subtraction. All right, so let's highlight a few things here. You're going to be solving for Gibbs free energy, everybody. Delta G is what you're going to be looking for. Delta G is the difference, as I've underlined, between the change in enthalpy and the product, which is multiplication, of temperature times entropy. So here is the final equation of your chemistry lives in high school, unless you decide to take AP Chem. And if you decide to do AP Physics, there is some Chem in there. I can tell you in AP Bio, there's some Chem. Not a whole lot. If you take chemistry, as you all are now, those parts in AP Bio that require Chem will be easy. Here they are. Now, in case your eyes might be playing tricks on you, I want to be sure that you understand what this is. This is temperature times the change in entropy of the system. Okay? Sometimes I can play some tricks on some students' eyes and you don't, T delta S, what the heck is that? Temperature times the change in entropy. Yeah. You're not going to have a changing temp, it's just going to be the same. Okay, now as far as units of measurement are concerned, this is Gibbs free energy. Energy is the key word here. So what is our unit of measurement for Gibbs free energy? Joules are bigger. Kilojoules. Your unit of measurement for Gibbs free energy is going to be in kilojoules. I indicated this earlier. It's in the writing here. What will be our unit of measurement for temperature? It's going to be in Kelvin. Remember that Kelvin is your temperature in Celsius plus 273.15. I've told you in the past I'm not going to be that big of a stickler when it comes to the 0.15 part, but definitely don't forget the 273. Okay? Enthalpy is going to be kilojoules. And then we have the entropy of the system is going to be joules per Kelvin. All right? Okay, let's talk about reaction spontaneity when it comes to Gibbs free energy. If the sign for free energy is negative, the reaction is spontaneous. That's delta G, not necessarily delta H or delta S. This is delta G. So I'm going to make a data table for you guys to really organize your thoughts so you can definitely have all this straightened out. As far as is the reaction going to be spontaneous or non-spontaneous? So let's make a little graph here. After I'll give you a moment to get caught up. All right, here we go. It's not a graph so much as a table. Okay, you're going to need 5 rows. And you're going to need 4 columns. All right. First row is going to have delta H, delta S, delta G, And then the reaction spontaneity. Is it going to be spontaneous or non-spontaneous? Or under what conditions would it be one or the other? All right. If your change in enthalpy is a negative value, your change in entropy will be a positive value because all that heat is going towards the environment. This means that delta G will always be negative. And this reaction will always be spontaneous. What's that? Yeah, because if you're losing heat, where's that heat being lost towards? Right, and that's making it more disordered. All right, next row. Let's say that you're changing sometimes I gotta stop myself. Am I gonna say entropy or enthalpy? H is enthalpy, if that's negative. And the change in entropy is negative. Then delta G could be negative or positive. This will only be spontaneous at lower temps. Next, we have the change in enthalpy is going to be positive. The change in entropy is positive. This means the delta G could be negative or positive. And it will be spontaneous at higher temps. And then last row, change in enthalpy is positive. Change in entropy is negative. Change in Gibbs free energy will always be positive. And this will never be spontaneous. So I'm going to give you guys a practice problem. You can refer to this data table and make your conclusion on whether the reaction is going to be spontaneous or not. Okay? And when we say not spontaneous, or it's not going to be spontaneous, you can just say non-spontaneous. So you may have one or two problems like this on your test. Your test is 32 questions, by the way. And that will be on Friday. Other than your test and your review, your grades are all up to date. I have to also mention that. Give you guys a moment to finish looking this over. The Unit 16 review that you submit on the day of your test. All right, and let's do our final practice problem of the year. You okay, Emma? Mm-hmm. Example problem number 7. Determine reaction spontaneity. I would like to indicate, I'm going to put this up here. Don't forget this equation. There are 4 variables. You will obviously be given 3. You just have to be sure that you've matched them up with the right variable. Here we go. For a process, your change in enthalpy of a system is 145 kilojoules, and the change in entropy of the system is 322 joules per Kelvin. Is the process spontaneous at 382 Kelvin. Okay. Well, let's match up the equation I wrote up above with your actual variables. Looks like we have our delta H, which is your change in enthalpy. That would go right here. We have your change in entropy, delta S. That would go right here. And it looks like we have your temperature, which will go right here. So as you all can see, it's just a simple multiplication and subtraction problem. All you have to do is plug in your variables. Now, I do see an issue here. It's not going to be as simple as subtracting and dividing. Looks like Arshawn already sees. Do anyone else see an issue here? Kevin sees it, Juliana sees it, and Arshawn sees it. Anyone else? If you're a little lost as to what I'm alluding to, I want you to look at the units of measurement for your known values. Scott, are you nodding your head? Do you see it? Okay. Kendall, what is the unit of measurement for the change in enthalpy? What does it say? For this problem, what is it? 145 kilojoules. Good. I want you to tell me what is the change in entropy of the system. What is that measured in? Aha, joules and kilojoules. Have you ever run a 5K in your life? Do you know what a 5K is? What is a 5K? But what does the K stand for? Yeah, you could say I'm going to run 5,000 meters, which is the same thing as 5 kilometers. Well, Kendall, let me before we answer, I want to throw this at you. What is the difference between running 5 kilometers and 5 meters? Do you know how long a meter is? I know that you were born and raised in America, so you're not used to the metric system, but a meter is a baseball bat, roughly. It's about 3.2, 3.1 feet. If you ran 5 meters, that would be like going from me to Kevin. Is that very far? No. But when you run 5 kilometers, that's running 3.15 miles. So you see the difference between just a meter and then 5,000 meters. So would it be appropriate if I were to say this? I'm going to say Kevin is going to run 5 kilometers. Carson is going to run 5 meters. So 5 kilometers plus 5 meters. Here's what I have seen done time and time again. Would I be accurate in saying that the two of them ran 10 kilometers? No, because you're not using the same unit of measurement. So what you guys would need to do is you need to convert one of these into the other. Should we convert kilojoules to joules? Or should we convert joules to kilojoules? What do you think? Let's convert the joules to kilojoules. So let's go way back to Unit 1, long time ago in September. Kilo means how many of the base unit, like kilometer, kilojoule, kiloliter, kilogram. How many grams in a kilogram? How many meters in a kilometer? How many joules in a kilojoule? Very good. So how many zeros are there in 1,000? There are 3. The decimal is theoretically right here. Which way should we shift it? We've already established that we need to shift it 3 places because there is 1,000, or there's 3 zeros in 1,000, and we need to shift the decimal 3 places. But should it be 3 to the left or 3 to the right? 3 to the left. So we're going to shift this 1, 2, 3. This is no longer going to be 322 joules per Kelvin. We're going to make this 0.322 kilojoules per Kelvin. It is so important that you use common units of measurement. Common units of measurement. So we now have everything that's in the same unit of measurement. It's on the same scale. We can now get to work. So change in Gibbs free energy will equal 145 kilojoules minus 382 Kelvin times 0.322 kilojoules per Kelvin. I hear those calculators opening up. Let's show our work on this. We have 145 kilojoules minus I have about 123. Now, what is going to cancel out here? What unit of measurement? Kelvin is gone. I thought I heard somebody say kelvins. Don't say kelvins. It's always singular. Like we don't say it's 98 degrees Fahrenheit. We don't say that, so don't say kelvins. All right. 0.004. I'm not going to really bother with 0.004. That's minuscule. Okay. And so we now have pretty easy math. 145 minus 123. This is going to equal 22 kilojoules. Is this going to be positive or negative? It's positive value. So the fact that this reaction is going to result in a positive value for free energy, is this reaction spontaneous or non-spontaneous? You would say that because this is a positive value, it will result in the reaction to be non-spontaneous. So I want to emphasize to all of you that you can't just say, oh, it's 22 kilojoules. What does that mean? Well, because it is a positive value, it is going to be non-spontaneous. Which means that if this reaction were to actually happen, you would need some like outside influence, something to help it proceed forward. Yes?
If, I have a question about like the chart. If a system is taking in energy, how does disorder increase?
Because you're taking in energy from other reactions. That's the second law of thermodynamics. Reactions naturally lose energy from one transfer to another, and that just contributes to it. Okay, so, and I do want to refer to that table real quick, guys. Emma, according to this problem, what was the value of the change in enthalpy, positive or negative?
Positive.
Okay, so let's look back up here. There, all right, we're down to these two. Max, according to this problem, what was the value of your change in entropy, positive or negative?
Positive.
It was positive, so we want to look at this one. And so Gibbs free energy could be positive or negative. It said that this reaction will only be spontaneous at high temps. This must have been at a lower temperature. That's why it's non-spontaneous. Okay, and that concludes our unit on thermochemistry.